All right, let's get started. Can you hear my audio? All right, thank you, Claude. Good morning, all. My name is David Ruck. I'm here at the University of Maryland in Baltimore, Maryland, and welcome to Cytometry in R. And today we're going to be talking about how to apply transformations. So we're now in the 7th week of the course, and we're going to take a closer look at how we can take the raw values that our FCS files arrive with, and then transform them, i.e. scale them in different ways. Did we lose the audio? Double checking. Can we confirm if you can hear my audio or not? All right, let's try that again. So in the seventh week, we're looking at how we can take our raw values of our FCS files and basically transform, i.e. scale them in different ways, so that we're better able to visualize both the positive and the negative populations that are present within. So there are several commonly used transformations when it comes to flow cytometry data. Typically, there's also a couple that we are using in context of mass cytometry or cytoth data. Most often you'll see like the R-sign transformation. Regardless of which transformation method we're choosing, the goal kind of remains the same. We want to rescale the data in a way that allows for better interpretation. The reason for this is oftentimes flow cytometry data, the things that are what we consider as negative are kind of linear in scale in that region. But for cells that are staining with antibody, they can be logs the difference between the dimly positive cells and the brightest positive cells. So we want to be able to kind of compress this logarithmic space into a more linear fashion so that it's a little bit we're better able to interpret it. So a misapplied transformation can end up being dangerous when it comes to our data analysis. So we shouldn't just accept the defaults. We should always try to tinker with it to make sure that it's actually visually making sense. Likewise, this approach is shared by many exploratory data analysis protocols, so it's something that we'll be seeing throughout the course as we move forward. Additionally, we have near perfect timing this year because the Cytobytes, which is the ISEC-led Education Committee's YouTube channel, Felix had a really good video out about how to transform data and some of the theory behind it. So I recommend everybody to follow the link to just take a look and see how it looks. As we do every week, I have updated the course repository folder with the new data for this week. So if you haven't yet done so, please sync your forked version of the Cytometry in R course folder to bring in the most recent updates. And then going to your local computer within Positron, pull in the local changes to your computer. Once everything is set up, if you're following the organization scheme of the course, basically copy over the contents of the data folder into your week 7 project folder, and that will help prevent any merge issues from occurring in subsequent weeks. So this week we're going to be using extensively the Flow Workspace package. So we're going to be calling multiple functions from within. So if you remember where we had left off a couple weeks ago for week 5, we had been starting to work with gating set objects, but at that time we were bringing in a FlowJo workspace using the CytoML package, bringing those into R as fully assembled gating sets. And we kind of left it there because we were running out of time on that particular day. But this is basically continuing where we had left off there, but we're basically building our own gating sets from scratch and seeing what the different elements are. Likewise, we're also going to be using the ggCytoX package quite extensively throughout today. So it was going to make sense just to go ahead and load both of these packages right from the beginning, attach them to our local environment via the library call, just to make sure we have access to all the functions. Now, we're going to be working with two separate data sets today. We're going to continue with the spectral flow cytometry files we've been using for the last few weeks, namely those 6 unmixed FCS files that were first shared back during week 5. This time, as I mentioned, we're going to be building the gating set from scratch rather than bringing them in through the CytoML package. All these spectral flow cytometry files have something in common. They have 2025 as part of their file name. So when we're going in and using list.files, we're going to be identifying them based on the 2025 shared portion of the name. Likewise, we're also going to be working with the mass cytometry or CyTOF dataset. So for those of you who primarily do mass cytometry, who have patiently waited for the first 6 weeks of the course, wondering where your mass cytometry data is, we finally got to it today. I'm using 3 FCS files that I ended up borrowing from the import repository, namely the study SDY2739, which was a study that looked at clinical immunity to malaria, looking at some epigenetic markers. So these mass cytometry files have the G1_2 portion in their file names shared. So we're going to use those that part of the name to distinguish them from the spectral flow cytometry files. So just remembering what we've done previously, if you're keeping the organization scheme of the course, we're basically looking within the contents of our data folder, which is where we have stashed these FCS files. And we're creating our first file path to the object variable we're calling storage location. We're then using list.files to check within storage location to return all things that match the pattern.fcs. And because we want to make sure the full file path is present, we're setting full.names as true so that our computer knows how to go from the working directory down to those FCS files. Once we've created this big FCS_files vector, we're going to subset it to be able to identify out just the spectral flow cytometry files, also known as SFC, or just the mass cytometry files, which I'm abbreviating MC for the rest of today. And basically we're doing something we've seen similarly in the past. We're using the stringer packages structure detect. We're checking within the individual vector contents of FCS files, and anytime it finds something that has a 2025 in the file name, it's going to come back as true. And because it's within the square brackets, it's going to index them and isolate them out separately. And a similar process would happen for the mass cytometry files. Anytime it detects a G1_2 in the file name, it will end up subsetting them and returning them to our new isolated out vector. So let's first get started using the SFC dataset. So let's first go ahead and double check that our subsetting did actually work, that we just have the SEB files, the spectral flow cytometry files. So we check SFC files and we can see, yes, everything that had 2025 got correctly isolated. The reason we do this is because Flow Workspace, when you're creating a gating set, expects all the files present within that gating set to have the same kind of parameters, the same kind of number of columns. In this case, your flow cytometry dataset and our mass cytometry dataset have different floors or metals respectively. They have different numbers of each, so they would cause a conflict and would come back as an error out. So circling back to what we did during week 5, when we looked at the differences between flow sets and cytosets, we saw that cytosets basically use less RAM memory because they're working through the pointer system. So we're just going to go back and borrow those lines of code that we saw a couple weeks ago. And basically, we're using the load cytoset function from FCS to load in our SFC files, setting the truncate max range and transformation arguments to false. This loads into our cytoset, which we're then passing to the gating set function, which just wraps it around and creates a gating set object that we're able to use. So one worthwhile thing to just go ahead and check out at the beginning of the day is check to see what metadata is present within our gating set, which we can do using the pdata function as we saw previously. And as you can see, when we're bringing it in this way, it's kind of bare bones. We have row names for each individual FCS file that's present, but the only column we have is the name, which contains the full file path. So in terms of additional metadata, we don't have very much at this point in time. However, if we're looking at the file name, we can see there's additional information present. We can see the date of acquisition for this particular file. We can see the specimen ID number right there for infant. And then we can see the different treatment conditions for the individual tube, namely, were they controls or were they SEB treated? So there's a little bits of extra pieces of information we could actually use if we're able to get them out of the file name and into the actual metadata. So one thing that we should do is we need to try to retrieve out this contents in the metadata so that we can use some of those dplyr package functions to kind of clean them up, to make them as additional columns, so that we then have a control condition, we have a condition column, we have a specimen column, we could have a date column, things of this nature. So if we're starting to actually change the existing metadata, remember our dating set object is one of those complicated S4 style objects from Bioconductor. It's not going to be quite as easy to edit in place. Oftentimes it's better to extract the data and then be able to work on it locally on your computer. And then when it's ready and assembled, end up putting it back into the dating set. So the way we can do this is basically we just same function we use to call the metadata. We're just assigning it to an object variable we'll go ahead and call metadata. Now, if we look at it as it currently stands, we can see that this object we got back is basically the data frame object. And this is one that we can actually actively work on using all the dplyr functions we've learned about so far. And so if we're going to use a dplyr package, we need to go ahead and load in the attach dplyr to a local environment just so that we're able to use its functions. And while we're doing this, we might as well load in the stringer package because it has some functions that we'll be needing a little bit later on. Now, I never like writing on top of the actual existing columns, just because if you do a mistake and everything gets wiped, you have to go back and start again. So oftentimes what I'm doing when I'm editing metadata is I'm just going to duplicate the existing column to a new column that just has a different name. That way I'm able to make changes to that new column without actually affecting my ability to go back and try again if I need to. So in this case, if you're just duplicating a column, just remembering back to what we saw for week 4 with the tidyverse functions, we're working with our data frame, we're passing it through the pipe to the mutate function, and then basically we're setting up this new column called condition, and we're just setting it equal to our existing named column, which will come back and we'll now have 2 duplicate columns right next to each other. So if we went back and checked the actual file names, we can see they all have a common syntax up to a certain point. And then when it comes to the conditions, they come up in 3 different varieties, control, PPD, and SEB. And those particular conditions are located between the very last underscore and before the .fcs portion of the file name. So if we were trying to think of how can we extract out the relevant pieces of information that will eventually become this condition column, we basically are trying to get rid of all this first portion that's in front of the actual condition, and then get rid of the .fcs that's found at the very end. So this is kind of like what we should be targeting as we start moving forward. So if we're thinking of what functions do we have that can help us actually extract out this information, we haven't encountered any directly yet. So in base R, there are 2 functions, namely the sub and the gsub function, which are often used to actually extract out a particular pattern. So the way that these 2 functions work is basically you provide a pattern to match, kind of similar to what we've seen for list.files, and then you provide a pattern with which you want to replace it. Now, if you don't want to replace it with anything, all you need to do is basically leave 2 empty quotation marks, and it's going to just go ahead and delete everything and not replace it with any value. So what sub actually requires when it comes to detecting a pattern and eliminating a pattern is what's known as a regular expression, also known as a regex in short. And I'll show you an example of what this looks like here, and I'll go through more of the explanation of what these individual dot asterisk underscore mean as we go forward. So if we're using the sub function and using a regular expression, we're basically giving it the pattern to match, which is dot asterisk underscore, which basically matches everything that's before that last underscore. And then we're replacing it with nothing, so we leave these quotation marks empty. And then we're operating on our data frame, specifically our condition column. And as you can see, that condition column that had the full file names ends up being abbreviated, and we're just left with the second portion of the file name after that last underscore, namely control SEB, control SEB. So as we viewed those particular ones there, we're not quite where we want to be when it comes to just having control or SEB or PPD as our condition. We still have that .fcs portion of the pattern as well. So what we could do is just rerun sub again on our intermediate product and get rid of anything that matches the pattern .fcs, replacing it with empty quotation marks, just so we are able to get rid of it. And sure enough, we can do that. So if we took that last one we just ran, saved it to an intermediate object, and then just ran again sub, using anything that matches pattern.fcs and replacing it with nothing, you can see we now have just the conditions that we're actually interested in. So One thing to note is that even with years of practice on my end, I still often struggle to remember what the proper regular expression syntax code is to match an exact pattern. This is because it can get complicated when you're trying to target a specific location, like what's the difference between the second and the third underscore, or the first and the second hyphen. This can kind of be a little dogmatic when it comes to actually building out a regular expression. However, one thing that's very useful is if you think of a large language model like ChatGPT or Claude, if you ask it a very narrow question and you are asking for something very specific, it's really good at quickly coming up with the actual regular expression that you need to do the substitution that you're trying to do. So for example, an example prompt you could use for an LM would be like, you need to tell it you're working in R. Specifically, you want to tell it you're using either the sub or the gsub function because there's a lot of different ways to do things in R. And then basically you want to keep everything after the very last underscore, and then it's going to figure out what it's going to try to do to actually get rid of all this portion of the name. So in addition to both the sub and the gsub functions from base R, we can also get a very similar outcome using the stringer package from the tidyverse, using namely the structure extract function. Now it uses something very similar to a regular expression. It's kind of like a regular expression inspired, but it's still very hieroglyphic. The main things to note in the next line of code I'll show is basically this little upward pointing arrow is basically denoting the start of your character string, versus the $sign is always denoting the very end of a character string. So in this case, with a pattern, we're going to see if it has something like upper pointing arrow underscore means the very first underscore being encountered, versus if it's .fcs $sign, it means the final part that matches .fcs. So if we check the large language model asking just to do that same kind of extraction in a single go, trying to isolate our condition, basically you'll get back this regular expression like sentence of code, which is saying the first part you're trying to get rid of is everything from the start to the last underscore, and then everything between that's being kept until you get to the .fcs portion. So as you can see, it's convoluted. It's not something I would want to try to remember off the bat, but it works pretty well at extracting out just the piece of information that you need from a file name. So wrapping this all together, we now have the regular expression. We need to either use sub or end up using the structure extract function from stringer to actually create out a condition column from our actual existing name. So if we saw how this actually looked like implementing it, we're taking our metadata, we're passing it through the pipe to mutate, we create the new condition column that's identical to name, and then we're passing it through the pipe to another mutate function where we're editing that condition column, basically extracting out just the condition part of the variable because it matches this pattern. And as you can see, our new condition column now ends up isolated just for the condition values that we're interested in. And fortunately, extracting out a pattern is much easier than trying to say grab this specific portion that's between these two alternate locations. So if you're trying to grab just the specimen ID number, we can do something very similar. The regex inspired code is basically match anything that has infant as a start, and then the last 3 digits will vary. And as you can see, just adding it onto our current line with an additional pipe, we get isolated out what we need to have. So at this point, we now have 2 data frame objects. We have our original metadata, and then we have the 2 additional columns that we have created separately. And our goal, if we want to add them back to the gating set, is we basically want to combine them together so they're a single data frame that we're then able to add back in. And the way we do this in base R is using basically the cbind function, which will combine the 2 data frames together. So what this would look like is basically we're doing cbind, and then within the parentheses, we're providing both our data frames, both metadata and 2 extra columns. And as you can see, we still have the column names present, the row names present. And then we also now have all 3 columns that we're actually interested in. So it's a much larger data frame than what we started. And then to actually overwrite the existing metadata within the gating set, all we need to do is assign it over. And the way we do this is just our little assignment arrow back into the same function that we basically use to retrieve the metadata. And this is how we overwrite the existing metadata and replace it with the actual ones that we're interested in. All right. Now, why do we do all this is mainly because it will allow us to actually go in and subset out files based on particular metadata conditions that we're interested in. So right now we only have 6 files, but if we had 140 FCS files and we only wanted those that were treated with SEB within the gating set, having that column within metadata would be useful for doing things. So the way you would basically subset a gating set in R is if you use the subset function, you provide the name of your gating set, and then the particular metadata condition column that you're interested in, and then we're using that percentage in percentage operator, and then we're just matching anything that has the pattern that we're interested in this case SEB. So you can see in this case we subset it down for just the FCS files that were SEB treated. All right, having emerged from metadata in our first encounter with regular expressions, let's go back and start looking at our SFC dataset, just trying to get ready to actually apply the transformations that we're interested in. So just remembering what we have our gating set, which has 6 FCS files present. And one good thing to know, especially if you're trying to transform, is we're going to have a lot of different parameters present within an individual FCS file. Not all our FCS files are the same. Some may have different fluorophores. It's good to remember what you have, especially if you're working with data you grab from a repository that you have not encountered previously. So the way you can check to see what the actual fluorophores present within your gating set are using the column names function. Because if you remember, the actual fluorophores are saved as individual columns, so we're still able to retrieve out the names of the fluorophores by using column names. And sure enough, this works. As you can see, this was, I think, a 32-color SFC panel, and there's also the time and side scatter, forward scatter parameters, side scatter and forward scatter having both area, width, and height as well. And we also do have side scatter blue because this was an aurora. Likewise, it might be useful to get out the actual marker names, not just the fluorophores. And rather than do what we've done in the past, where we broke into the S4 style object, grabbed the parameter data frame, and then brought that in, we could just use some of the work that the developers put in and use a actual function, helper function, to actually do that same process. In which case, we could use like marker names as the function to do in this case. And sure enough, if we do this, we get back what looks to be like a named list. As you can see, we have the fluorophore still shown, but then the actual value underneath corresponding to the markers is showing up. So this is a named list, kind of like what we've encountered in the past. And finally, we should just go ahead and make sure that ggcyto is still working, that all our updates to both ggplot2 and ggcyto are still compatible with each other. And let's just go ahead and plot forward scatter, side scatter. So if we go back to the code we had from the ggplot lesson, just go ahead and paste it in. Sure enough, we're able to visualize just the basics of our first specimen in the plot. So please note that when we did this for ggcyto, we just included a single square bracket right after the gating set name, so that we're basically indexing for the first FCS file present. One important thing just to continue reiterating is that if you check str for this particular line of code, you can see we're still working with the gating set. We haven't subsetted down to a different type of object, which is important. So if you had accidentally, for example, included double square brackets, you would have actually broken into the S4 style internal, and you'd have gotten back what's known as a gating hierarchy, which more involved in the gates. So just always be aware of what you're passing to a gating set or to a plotting function, just because this can matter, especially if something comes back and it's not working as intended. So far we've only visualized forward scatter, side scatter, which are kind of on a linear scale, so they're not necessarily going to need to be transformed. But let's go ahead and check a couple of the fluorophores, those that we would normally associate as needing to be transformed. So within our untransformed data will look very similar like this. So you can see the CD4 is very, very narrow, very, very stretched out along the x-axis, looks nothing like our typical flow plots. And our CD8 values are a little bit more discernible, but they're still kind of squat and across the board. So this is an example of what untransformed data looks like, coming straight from like a spectral flow cytometer with no actual transformations applied. So there's so much space being occupied by cells that are positive. The goal of our transformation is basically compress these down so they're actually workable, so we're able to get better resolution on the more linear portion of the scale right around the negative values. So by contrast, if you think back to what we saw when we brought in the Flowjo workspace via the CytoML package, the exact same specimen had a visualization much more like this. The reason for this is most of the commercial softwares end up applying the transformation directly, so you never really ever see the back view of the untransformed data present. Now, if you want to check to see if a transformation has already been applied in the context of your gating set, you can use the gh underscore get underscore transformation function to basically be able to check. Right now, there's absolutely nothing present, so you see nothing is being returned. We just have this empty list value currently being shown. Now, Flow Workspace provides us several default transformations that we can be able to apply, but it also allows you to create your own if you want to do some weird kind of math. The functions in question are basically what we know as transformer-style objects. They'll contain lists of the required information that needs to be used when it actually comes to transform your FCS file. So if you look at some of the common default transforms, there's logical, which if we assign it to an object and then peek behind the curtain using the str function, we can see that this transformer-style object is just a list of 9. It tells you the name, it tells you what the transform and the inverse transformation is to be able to go back to the original state. And it gives you a little bit more information about like the breaks, the tick marks that you would expect to see for this transformation. Likewise, if you're more used to the bi-exponential, that's also included in the default transformations. If you check behind the curtains using str, you can see that it has different values that we typically associate with some of those more GUI interactive functions, like if we're working within FlowJo or FCS Express, where it shows you the channel range, the max value, the negative, the positive decades, and then the width bases being applied. And then you can also see here's the inverse transformation, which is what you use to go back to the way it was before you did the initial transformation. And if you're doing mass cytometry, you're more likely to be using one of the assigned transformations. And similarly, it's also a list where all the different variables that you're specifying get transferred over. And there is an additional assigned transformation as a default. So as always, it's worthwhile to try to check the help documentation before you're doing anything, just to make sure you actually understand what the arguments are and how these will be used within the setup as far as we go. So first off, we have found there's several default transformations that we can be applied, but we don't want to apply all these transformations to everything. We don't want to transform our time parameter. We don't want to transform the forward scatter, the side scatter blue. These are all things that probably should be kept as they exist, not actually being moved around. So we need to be able to subset down which columns we want to be transformed and which columns we don't want to be transformed. So the way we can do this is going back to the column names function. We saw that we can retrieve out the column names. And currently we have a combination of both floors that we want to transform and those parameters that we don't. So basically we just need a way of subsetting out the time, the side scatter, the forward scatter parameters so that we're not actually including them within our vector style list. So what we can use is something we've encountered a little bit in the past, namely we can use the square bracket index method, but then use the stringer structure detect in combination with the exclamation sign, which as we saw basically flips the value, to be able to remove out anything that matches a particular pattern. So for this particular line of our code, basically remember, we're working with our vector list of FFC parameters. And then within the square brackets, we're using structure detect to find anything that matches the pattern forward scatter, pipe, side scatter, pipe, time, with this pipe basically denoting OR in this particular context. So anytime it goes through a value in the text up and that's forward scatter, it's going to come back as true. But because we have that little exclamation sign at the front, it flips it to false, which means it's not kept and is actually excluded from your vector. So if we end up running this line of code, we'll get back just the floors, and we'll have excluded out time, forward scatter, and side scatter from our list of floors. Now that we have the floors that we actually want to transform and our particular default transformation we want to apply, we need to kind of combine these two together into what's known as a transformer list, and which we're using the function transformer list. Now, this is kind of the way you would look at this right now is basically you're combining the floors you're interested in with the particular transformer you're trying to apply. You're creating this new object, my bi-exponential transformation in this case. And if you just print that statement to your console window, you'll see it's a list showing each of the floors they're going to be operated on, and then the transformer that's going to be applied to each accordingly. And this is how R knows not to go out and to check forward scatter, side scatter, because it's not present within this list. Now, if you're checking behind the scenes, you can basically see it's coming back as a named list, which each of the floors having its own list of actual transform parameters present underneath. So this is useful in case you wanted to apply a slightly different transform for a couple markers while keeping all the others similar. You just need to figure out how to do it within the context of this list style object. And similarly, here's an example for just APCA. So as we go forward, the last step is basically we need to take this transformer list object that includes the floors and their transforms to be applied, and actually apply it to our gating set. And the way we're doing this is basically using the transform function, specifying our gating set, and then specifying the actual bi-exponential transformation being applied, and sure enough, it's going to transform our data. The one thing to note is gating sets work based off of that pointer system. So they're kind of like writing on top in place, so you're not actually assigning this to a new object, which is why the line of code looks like this. We'll see another example of this as we go forward. But let's just go ahead and check to see what this default transformation did to our actual plot. So if we go ahead and rerun our plot numbers, we get back a plot that looks like this. So now the values are not all concentrated around the x, and they're not all concentrated around the y, but it still doesn't look quite like it should for a flow cytometry plot. So this is one of the reasons never to just go with the default option. It's not actually going to be representative of what you need to do. We're going to need to tinker and adjust with this just a little bit more to get everything to work out well. So one thing that we can do is check to see what our transform function options are in terms of the optional arguments. See what the default values are that are not quite working in this case, and then figure out by tinkering around what do we have to do to actually get them into place. So as we're always trying to do, if we need to find particular information about a particular function, we can use the help file. So if you're within positron, you can just hover over the function name, or if you're working within your console window, just add a question mark in front of the function name, and this will be able to go in and look up that particular set of information. So in this case, let's start by looking at FlowJo by exponential transformation function. And you can see it comes back with a little bit of a help documentation, but right off the bat, it doesn't seem to be providing much information. It gives you two arguments, ... which says parameters passed to FlowJo trans, and then n specifying desired number of breaks, which doesn't seem quite right. So what we're encountering right now with this help page is basically this particular function that we're working with is not the main function that's actually doing the work. It's more of a wrapper function that gathers the bits and pieces and then sends it to the correct function, gets back the output, and then returns them to you. So it's kind of just the intermediate function between you and the actual function you're interested in. So in this case, it gave us the information of the actual function that's doing the hard work, namely the FlowJo trans function. So we can just go back in and look up that specific function in the help file. And sure enough, this looks a little bit more like what we'd expect. It gives us various different arguments and what these arguments correspond to. And then if you look under usage, you can kind of see each of the values that's shown in this like pink purple for my screen. Those correspond to the default values that the functions ends up applying to your actual data. So let's start out by trying to get our plot to look more like the flow cytometry style data that we expect to have. So we should start by modifying the arguments and just kind of see what effect each of these arguments has on the final visualization. So when we are basically going to be going back in and overwriting an existing transformation, because of how that pointer system works, once you've already created a transformation, it's kind of hard to get the gating set to let go of it and then be able to completely write again anew on top of it as is. So one thing I find much easier to do is just basically go ahead and reload in the entire data. Go ahead and reload in the entire gating set. The reason for this is those pointers that had been created to the original location on memory end up getting deleted, and that you're then able to create a new one right on top of it. So in this case, we're just repeating the same line of codes we saw already. We're loading in our cytoset from those particular files. We're creating our own gating set, and then we're basically using those default parameters we have already specified to create our transformation. We're combining it with our floors of interest to do that transformer list, and then we're passing that new updated transformer list to the new gating set that we're just retransforming in place. So if you remember right now, our default using all those default arguments looks like this, and it doesn't look quite right. We have all these negative values, and the area around 0 is not really being compressed well, so it seems to be just the negative portion that's kind of being dragged out as we see. So one thing to also go ahead as we do these little adjustments is just check back sporadically on our GHGetTransformations function just to make sure it's actually applying things correctly as we move forward. So if we look at it in the context of the BUV805 floor right now, we can see there is a function applied. It gives you the actual math that's happening in the background, and you can see the actual parameters as far as the defaults being applied in this current context. So before we go messing around with the other settings, let's go ahead and tackle width, because more often than not, when you're working with Flow Workspace, this tends to be the one that the default ends up missing most by when it comes to spectral flow cytometry data. So normally working in FlowJo or like FCS Express, I often have mine on the bi-exponential like transform, and generally my width basis compressing the negative is something around either negative 500 or negative 1000. So let's go ahead and switch out that value in our current settings just to see what happens to the visual. So when I rerun all this line of code, you can see that down here on width basis, instead of negative 10, which was the default, I've now changed it around to show negative 1000. I proceed to create the gating set all over again and retransform it. And then when I run my line of code to plot, you can see it looks much more similar to what we had a couple weeks ago when we brought in directly from FlowJo via CytoML. The negatives are no longer being stretched out quite as dramatically. They're nice and there's a good resolution on the negatives. We can see the CD4 is still a little stretched out, but it's still workable, and we can see distinct positive and negative populations for each fluorophore. So it does look like the width basis was off, and that was what was causing the very dramatically different plot that we were getting back previously. Let's go ahead and check a couple additional argument numbers for width basis, because we just tried for negative 1000. Maybe we can have a better visualization with something else. So I will go ahead and half the amount. So I'll just read width basis equal to negative 500. And just rerunning everything again, you can see the CD4 has become a little bit more compressed. However, the negative is starting to spread out just a little bit, so it's still good. I can still get this resolution on my particular populations. It's going to vary what your intended goal of analysis is between if you choose negative 500 or if you're choosing negative 1000. So let's also just be completionist and check to see what the next value down would be. So let's go ahead and try something like negative 100 and just rerun our lines of code. And as you can see, CD4 positives are now very nice and concise, but we have this massive spread happening on our negative. They're not being compressed nearly as much. They're occupying much more space of our plot in general. So we know negative 100 for width argument is too far in the opposite direction. We need to keep somewhere around the 500 or the 1000, negative 1000 range accordingly. All right. Now that we have a parameter that we'll keep for width, I would say somewhere in the line of like negative 500 for the next couple tests, let's see what the other arguments do when we start changing their parameters. So our current channel range is set to 496. This is often instrumental. Let's go ahead and double it just to see if there's any effect. So as you can see, we're now keeping width basis negative 500, but we've doubled the channel range from 496 to 8192. Let's see if this has any effect on our visual. By eye, it doesn't seem that much has changed compared to that last one we had for negative 500 width. Let's go ahead and check to make sure that the actual transformation was actually being applied. And if we scroll down here, we can see the channel range was indeed changed, and now it's set to 8192. So it wasn't like we didn't actually run the line of code or it ignored our change or something like that. So let's, instead of doubling it, let's go ahead and half the amount to see if we have any change in the visual. So as you can see, we now have channel range set for 2048. And similarly, I don't see very much changing within our ggCyto plot. So it doesn't look like channel range is misset. It doesn't look like it's being dramatically affected, at least within the context of what we have. So we can probably just keep the default as we currently stand. And just to double check, sure enough, we have indeed changed channel range to 2048. All right. Max value, the current max value is showing as 262144. So this is one that if you actually have done transformations on your different instruments, you'll often see those values listed. It kind of lands roughly in the same section you see the number of positive decades. So this is likely one that if you have that information from your instrument, copying it over will be quite useful. But if you're working with somebody else's files and you don't have the instrument handy, you may need to try to figure out what the best value is by trial and error. So if it's currently set for 262144, let's see what happens when we end up doubling it. So as you can see, width is still at 500, negative 500, channel range is back to its default. We ended up doubling this max value. And as you can see, we're starting to phenotype something that we saw when we had the width basis set to negative 1000. We still have good compression on our CD8 population over here, but the CD4 is starting to be stretched out. So definitely looks like max value does impact when it comes to our visualizations. Vice versa, let's see what happens when we end up reducing the max value. In this case, we are dropping it down to 131, 032, and sure enough, we are now having a spread happening on our negative population. So both max value and width seem to be able to directly impact our visualizations, and they also seem to be somewhat interconnected to each other. So this is kind of one of the things we need to be careful of the changes we do to one, because they may affect the other one downstream. So seeing as we could make changes to it and it was going to be jumping back and forth, let's just go ahead and leave it where we had it so that width is doing the main change to our plot, not so much the max value itself. Similarly, many instruments would give you different options for the number of positive decades that are being displayed. In this case, the default is set for 4.5, but I know different instruments will do 5 up to 6. So let's go ahead and see what happens, what it looks like right now when it's set to 4.5. You see, very similar plot to what we've had. But let's just go ahead and walk it up to like 5, increasing by 0.5 to see what happens. And sure enough, you see we start phenocopying a little bit what we saw when width basis was set to negative 100. So positive, max value, and width all have impacts on our transformation. Oftentimes it's best to try to just grab these from the instrument. And if you don't have the instrument, just be careful when you're walking one of them because it will also potentially change the other. And sure enough, this is the other side. We can also have negative decades, and this is particularly relevant for spectral flow cytometry data, especially if your data is messy and you have unmixing errors that are shooting to the negative and going out to like negative 10 to the 4th. We can add additional negative decades using this argument. So the default is currently set at 0. As you can see, our plot looks kind of like this. But let's go ahead and see what happens when we add in a little bit more. So let's go ahead and increase it to negative equals 1. In which case you can see it's starting to spread out a little bit more, but it's still quite discernible. The resolution is good. But if we start adding 2 extra decades and rerun the entire line, you see it starts spreading out a lot more. So as you can see, we have ways that we can customize our plots if we need to for particular specimens, but applying them generally across the board may not be advisable for everything. So to recap this portion for spectral flow cytometry data, we've looked at the various arguments, how they affect the overall visualization, and we've seen how some of these are interconnected with each other. Therefore, it's often worthwhile just to check your instrument settings and use those first. Alternatively, if you're working with repository data or from a collaborator and you don't have that information, just be cautious as you walk one value because they may affect the other values accordingly. Alright, so far we just looked at the bi-exponential example for spectral flow cytometry data. Let's turn and look at the mass cytometry, the CyTOF dataset, just to see how the R-sine transformation works in that particular context. So same thing, once again, we need to make sure we have just the files that we're interested in. So if we print the file that we created earlier, we see that it's just the G12s being included. So this is our mass cytometry dataset. And similar to what we've been doing, we just need to go ahead and load them into their own separate gating set. Load cytoset from FCS to create the cytoset, gating set under the cytoset to create a gating set. And then same thing, we need to figure out what the actual metals that are present within this particular dataset are. So we can do that using column names as well. And we get back all the different metal isotopes that are present. In this case, it looks like we go up to about 49 different metal isotopes for this particular panel. And likewise, we need to grab the corresponding markers that are associated with each, which we can do using the marker names function. And as you can see, many of these are more towards the epigenetic as far as different modifications go. But then we do have a few actual cell markers present. We also end up having beads and barcodes that we may not actually want to transform because they're more on the data handling side. For those of you who do mass cytometry regularly, you know the processing protocols that we actually experience. So for now, let's not actually try to clean up out beads and clean out the doublets and do the barcoding work. Let's just visualize what the data looks like as currently is, looking at the CD8 by CD4 plot. And as you can see, there's a lot of values that are kind of gathered around 0. That's a little bit what we expect from mass cytometry, but the visualization of the positive populations is really hindered as it currently stands as untransformed data. So we still need to apply a transformation for our mass cytometry data set. So we may not want to work with our particular markers. So in this case, let's say we want to exclude out the barcode and the bead entries for now, just as we don't want these transformed. And the way we do this is kind of similar to what we had done in the past. We can use the marker names function in this case because we want to exclude out based on the particular values that are present. So in this case, this retrieves out all the different named lists that we have. And then within these actual values, we're excluding anything that has barcode or beads through the use of this negation symbol within the square brackets. And you can see we're just ending up with our metals of interest in this case, corresponding to a bunch of the epigenetic tags and the different markers we're interested in. However, in this case, we need to get back the actual metal isotopes themselves, not the actual values. So we still need to have step. We don't want the values like the CD3 to CD4. We actually need the name of the metal. However, we're working with a named list. So what we can do is use this names function, which will basically just keep the named portion of the list and leave the values out. In which case, that's how we can go about getting out the individual metal names that are going to be used for the transformation. And once this is done, we can do a very similar process to what we did for the spectral flow cytometry data. We're creating a transformer list by providing the transformer of interest in combination with the particular metals that we want to transform. Once we get this transformer list, we see it's a list of a list style format, and with the particular arguments that are being applied. And then once this is done, we're just applying it to the mass cytometry data set, transforming the data in place. And if we rerun our last plot, we can see it's much better resolution when it comes to the CD4 and CD8. There's still some additional tinkering to do because we're working with the default, but it's not as directly adjacent to the X and Y axis as they used to be. So looking up the asign arguments, same kind of procedure what we did for the bioexponential. We can look it up, but we can see this is also a wrapper function. It's not actually providing us the actual one in place, but you can see the actual function that's doing the hard work is this flowgel underscore facine. So we can just end up looking up that function, and we can actually come back with the arguments that can be changed. So as you can see, this first argument is set to 4, corresponding to the numeric full width of the transform display. The numeric maximum value is t, in this case is set to 12,000. Additional negative range is set to 0.7, and length of numeric value is set to 256. So if we are basically going to be tinkering, let's just go ahead and rerun the code to create this gating set each and every time. These are the default arguments. I've copied them over so that we're able to modify them. And as it currently stands, our plot looks somewhat like this. And I won't go through all the arguments, but also just double check to make sure the transformation has been applied for this particular metal isotope. And we can see, yeah, it's been applied. It's not returning as an empty list. So let's see a couple of these arguments. Let's not go through all of them today. You will have time to tinker on your own if you're working with mass cytometry. But the current M argument standing for those asymptotic decades is set to 4. We're getting back a plot that looks kind of like this. Let's go ahead and increase it to 5 to see what happens. And sure enough, if we plot, we see that's no longer actually right on the 0 values around the axis. It's starting to have some degree of separation out. And we're able to see like the CD4, the CD8, and the double negative appear. Vice versa, if we had instead set it to tree and run, you can see everything's a little bit more compact against the axis. So we can tinker back and forth depending on what we're trying to do for our mass cytometry data set until we get this to be good. And skimming these, because we are running a little short on time, we can increase the t value. You can see it kind of looks like this. If we decreased it, it kind of moved a little bit, especially in the orientation. You can tinker back and forth to see what works best in your context. Negative decades, most of the values in Cytop are clustered right around 0 anyway, so you're not really changing very much. But we can try setting it to 0, and as you can see, both of those plots were kind of similar to each other. There wasn't very much changing in the big scheme for that argument. And same thing happens when we ended up changing the length. At least to my eye, it doesn't change dramatically across the board. So far, we've been working at transformations mainly in the context of visualization, and this is important because a misset transformation can mean when we're drawing gates, we're misidentifying our positive and our negative populations. The other aspect we're going to encounter when it comes to transformation is in a couple weeks, when we're actually trying to extract out the underlying data set to be able to use it to generate spectral signatures of our floors for use in unmixing. So if we end up accidentally extracting out data that's transformed, it can affect the shape of our signatures and therefore the outcome of our mixing. So we always want to make sure those values are being untransformed. So how do we actually extract out a data from a gating set? It's a little bit more complicated, as I mentioned, because it's working on the pointer system. But basically, we need to step it back until we get a cytoset object, which we do using this gs_pop_get_data function. Basically, the subsetting is grabbing the very first sample. as you can see, it's now creating a cytoset that contains just that first sample itself. And then once we have it back to the cytoset, we can just use the express helper function we saw back from week 3 inside the FCS file to grab out the underlying MFI data. Now, if we look at this underlying MFI data, we see something, especially if you're used to looking at flow cytometry values, these all seem to be very close together within a particular range. This is kind of the first key you have that this data has been transformed and it hasn't been actually untransformed yet. So a big difference when working with data in R compared to like working with commercial software. Commercial software will often apply the bi-exponential or whatever transform on top of the existing layer, and you're just changing the visual appearance. You're not actually changing the underlying data. When you're working in R, it's actually changing the values that are present within the columns, which is why having that inverse transformation function set up properly is important, because that way you're not accidentally modifying your FCS file in that context. So if we wanted to actually use this data, if we were trying to do it for fluorescent signatures, it would look kind of odd when you're first glancing at it, because the values have actually been transformed. Instead, what we need to do is we need to keep the untransformed data, meaning we need to revert it back. And the way we do that is using the inverse dot transform is equal to true argument present. So if we go back to that extraction to get to the cytoset, we set this extra argument layer here. And then if we check the expression data present within our cytoset, we can see the values are a little bit more erratic across the board. So it's more what we expect to see for untransformed data. And as I said, this won't be particularly relevant for today, but in a few weeks from now, when we start working with those fluorescent signatures, we'll need to know how to make sure our data is not being transformed by accident. So the takeaways for this week, we have looked at the underlying data for transformation within the Flow workspace context, providing both the transform and column names of interest to create our transformer list, and then we applied these to our own gating set. We also investigated how to visualize our data and provide additional arguments to ensure that everything's being optimally transformed, rather than just accepting the default options. We also survived our first venture into looking at what a regular expression was and how to handle those. So oftentimes it's just easier to see what your particular instrument platform is and how it has its different range settings set to, and just try to copy those in when you're actually setting up your own R workspace for that particular instrument type values. However, if you don't have the advantage of having the instrument next to you, if you're working with a collaborator's data, or if you're pulling data from a common repository like import or flow repository, you want to be able to know what you need to do to adjust it to make sure you have a good visualization, but also be aware of some of the caveats of how some of those different parameters tie together with each other. And what determines a good transformation oftentimes will be dictated by what you're trying to do with the data, whether you're trying to do a supervised manual style analysis or a more unsupervised algorithmic style analysis. So next week there will be no class. I'll be presenting at the ABRF conference, so if you're around, stop by. I'll love to say hello. What I had planned to do for this particular week was a combination of both transformations as well as compensation for conventional flow cytometry. As you see, we're at the top of the hour, so there was no way I was going to be able to fit the compensation class in by itself. So I'm still deciding exactly what I want to do. I do want to cover compensation because many of you are only doing conventional flow cytometry. But I don't know if I'm going to make it a standalone one session to happen sometime over the next 2 weeks, or if I'm going to just kind of put it in front of the existing schedule, and then we'll cover compensation in 2 weeks, and then manual and automated gating the week afterwards. So I'll let you know which of these two I decide, but we will cover compensation in one form sometime soon. Also, as a heads up, next week I'll be sending out the first class feedback survey. So this is our very first year of doing the cytometry in our course, and any feedback that you can provide will help us make sure to address any areas that we're falling short of, both currently as you take the class, but then also how to improve it when it comes to making this data, this resource available to others who may be self-studying in the future when there's no active lectures happening every week. And I'll send that one out starting next week. And with that, we're at the top of the hour. I'm respectful for your time, so if you need to leave, feel free to take off. Additional resources for today. Today I was focused mainly on the mechanics of how to implement a transformation in R. I didn't have the time to explain what do you actually want to have in a properly looking transformed data. Fortunately, this is an area the community has provided a lot of good resources for already, so I don't feel as bad as just pointing you to the additional resources. Both Flojo and FCS Express do a pretty good explanation of their particular transformations they have in their software. I've linked a couple of those. Optimizing transformations for automated high throughput analysis of flow cytometry data was worthwhile checking out. The Spectre R package pipeline, which is maintained by Thomas, Felix, and Giovanna, they do a really good vignette for the data transformation section. It has a lot of good visuals explaining, especially more in the automated unsupervised analysis context, what you're trying to do. So I've linked their article there. Oliver Burton, with his Colibri Cytometry blog, also has a good scaling your data for dimensionality reduction. That's one I've linked in. As I mentioned at the beginning, the Cytobites channel has let out their short video about transforming cytometry data, which I've linked. And for anyone working with mass cytometry files, there's a really good article right here at the bottom, which will link to even several additional really good articles as well to show you what you should actually do in terms of your own workflows. And with that, the optional take-home problems for this week. We excluded forward scatter, side scatter, and time from our actual column names that we were operating on for the bi-exponential transformation, but these are oftentimes stuff that you'll accidentally include by accident. So go ahead and transform those particular columns and see what kind of wacky plots you end up getting. Same thing, we had time just to cover the bi-exponential transformation, but the logical transformation is also pretty common and pretty popular. So just play around with that one to see what the differences are compared to the bi-exponential when it comes to the visualization and the arguments. And a similar story for those doing mass cytometry data. There's two default assigned transformations within Flow Workspace package. Try both of them, see how they differ, see if one is better than the other, and try to figure out what the major differences are. And with that, we're at the top of the hour. If you have any questions, I'm here for a few more minutes. If not, I'll see you on the discussion forum. And if not, I will see you in 2 weeks for the next class.